Okay, so this next one is the second one. So let's see what this says. We are given three sets A, B and C, which are related to one another like this. That is, C contains B as a subset and B contains A as a subset. And also there is a bijection F from C to A. And then some sets have been defined using this function, this bijection F recursively. That means infinitely many sets have been defined, and the recursive definition goes like this. The first set D0 is the complement of A in B, which makes sense because A is a subset of B. And then the n plus 1 set is the F image of the nth set Dn for all n belonging to the set of natural numbers. So we have to prove two things. The first is that these Di, these sets are mutually disjoint. That means if we choose two distinct natural numbers n and m, then the corresponding D's are disjoint. They do not have any common element. And then there is another thing that we need to show, which is about a function that has been defined, a function g from A to B, that is from A to B, defined like this. If the input x belongs to at least one Dn, that means if the input belongs to this union, then the G image of x is defined to be just the F image of x. But if that is not the case, if the input does not belong to any of the Dn's, then G of x is defined to be equal to just x. We have to prove that this G is a bijection. And because of this bijection, once we prove this, it will show that the cardinalities of A and B are the same. So let's now see how this can be solved. It will be better if we draw a small diagram showing A, B and C and how these functions are given. So in the beginning of the solution, this diagram is not a part of the solution. If you want, you can make it a part of the solution, but it's just there for our understanding. So the situation is like this. We have A here and we have B here, which contains A, and we have C here, which contains both B and A. And it's given that F is a function from C into A. And in fact, F is not just any function, it's a bijection between C and A. So that means if we take any element of C, that element may lie here, or in fact in A itself, the F image of that element will lie inside A. So F is such a function. Okay, so this is F. That means from C we are going into A. And how are the sets Di being defined? D0 is just the complement of A in B. That means this is D0, this thing. D0 may be empty also. It will be empty precisely when A is equal to B. That possibility is there, or it may be non-empty also if A is a proper subset of B. Okay. But now, because F is a function from C into A, so what will happen to D1? By the recursive definition, D1 is nothing but the F image of D0. So if we take, already I have said that any element you take from C, its F image is going to lie inside of A. So if in particular you are considering all the points here in D0, then after all, whatever these elements may be, they are after all in C. So all the F images of these elements are going to lie inside A. So that's why one thing that we can immediately say about D1 is that D1 is a subset of A. The same thing can also be said about D2, which is F of D1, that is also a subset of A, and so on. This will go on. That is, in general, we can say this, that Dn is a subset of A if n is a positive integer. And this also says something else about the relationship between such dn's and d0, because all of these dn's are going to lie inside A and d0 is disjoint with A. So d0 in particular is disjoint with these dn's also, and that is the first thing we are going to write in the solution. So let's start the solution with that. So in the solution we write this. We note that D0 intersection Dn is the empty set for all n, for all positive n. Since D0 is disjoint with A, this is the reason, and Dn is a subset of A for all positive n. Okay. So that means whatever we needed to show about the mutual disjointness of these di's, that we have already concluded if one of them is D0. So that means now we need to prove that Dn intersection Dm is also the empty set if n and m are both positive integers but distinct. Say that is not the case. Suppose that this intersection is non-empty for some positive integers n and m which are distinct also. Okay. Now from this non-disjointness, that means they have some intersection, we can next conclude this. Then Dn minus 1 intersection Dm minus 1 is equal to the inverse image of Dn under F intersection the inverse image of Dn under F. Okay, but we already know that how such inverse images behave with intersection. This is equal to this, and this is non-empty. and the reason is this. We have non-empty since dn intersection dm is non-empty, because that's what that it's coming from our supposition. It is our supposition, and f is surjective. Do not forget that f actually is a bijection, so it's a surjection also. So because we are considering a non-empty set, an intersection that is a non-empty set, where in B, which is the range of f, so the f inverse of this non-empty set will also be non-empty, and that non-emptiness comes from surjectivity of f. But there is something else you must have noticed, which I am not, I haven't said anything about that till now, namely that, okay, we know that dn is equal to f of dn minus 1, but does it immediately say that f inverse of dn is equal to dn minus 1? In general, it won't say anything like this, but keep in mind that f is a bijection. So when you are writing this thing, f of dn minus 1, what actually you are doing is that you are looking at the restriction of the original function f to this subset dn minus 1 of capital A. And since dn is by definition the f image of this, so this is a bijection. The original one was also a bijection. If you restrict that to dn minus 1, then it does not lose its injectivity. It still continues to be 1 to 1. But now if we change the range from B to dn, then it becomes onto also. This restriction becomes onto also. So this function is a bijection, and hence from this we get this. Similarly, dm minus 1 is also equal to this. Okay. So now what we have obtained is that another such intersection where the suffixes are 1 less than the previous suffix values is also non-empty. So we can continue this process. Eventually what we will get is this. Or we can write one more step. Similarly, dn minus 2 intersection dm minus 2 is empty. Continuing this, we eventually have D0 intersection, non-empty, I wrote empty. This for some positive integer k. Okay, we understand that this is a reduction process in which the suffixes are getting reduced. But why shall we get a positive integer k? That is because, keep in mind that n and m were distinct. So as we are reducing the n and as we are reducing both of them, they will not simultaneously be 0. Whenever one of them becomes 0, namely the smaller one, the other corresponding one will remain positive. It is because of this inequality that we are having this fact that k will be positive. K cannot be 0. Should I mention this, because it's not immediately apparent why that is the case. At least let me just write note that n is not equal to n. But this is a contradiction. It contradicts what we understood in the beginning itself. But this is a contradiction. So our supposition is wrong, i.e. These are D, not N. All such intersections also will be empty for all positive integers n and m that are distinct. Okay, so we have proved one half of what is being claimed, and now the other half, but I think I already need some ink. Now the other half is about that function g. Unfortunately, there is a problem with this. We will first see what the problem is, and then we will try to rectify it and then solve the exercise. We will modify things slightly so that it works. It's just a printing mistake, I believe, nothing else. Now, since we are anyway going to see something about this other function g, so let us draw the figure here also. It's not a part of the solution, but for our understanding. Again, this is A, this is say B, and this is C. Now, how are we defining the function g? Let's just see once more. We have said that g is a function from a into b. Okay. So if we take an element of a, any element of a, some x here, then g of x is defined like this. It is defined to be equal to f of x if x belongs to this union, and is defined to be equal to x if x does not belong to this union. And what is our claim? Our claim is that this g is, we have to show that it's a bijection. Is there any problem with the definition of this function itself? No. Let's see how. So if you have your x here, then depending on these two conditions, g of x is defined. So what is d0? We are including the set d0 in this union. So d0 is nothing but this, the complement of a in b. This is our d0. So x anyway does not belong to d0. That is always the case because we are choosing x from A. But it may belong to some other di. That possibility is there because the other di's are all subsets of A. We have already seen that. So the conditions they stay like this. Okay, there is no problem with the conditions. Now, if it happens that x belongs to some other di where I is a positive integer, then the image is f of x. Okay, what was f? Originally, f is a bijection from C into A. So for this x, f of x is a unique element again in A and hence again in B because A is a subset of B. So there is no problem with this part. But if x does not belong to any of the di's, in spite of being in A, it may be the case that no di actually contains x. X is in A, but x lies outside of all the di's. Then the image is x. And where is that x? That x is after all in B. It is in A and hence it is in B. So here also we are getting a unique output for a given input. Here also we are getting a unique output for a given input. There is no problem with the definition of this function g. G is well defined, but there is another problem. We need to show that g is one-to-one and onto. It is in this onto-ness that there is unfortunately a problem. And the problem is this. Remember, I already said a while ago that D0 may or may not be empty. So in general, there is no reason to consider that D0 always will be empty. That is, A is always equal to B. A may be a proper subset of B. In that case, D0 will have something, some element. But the problem is this. You see, where are we getting the outputs? From this discussion of what the function g does to the input, either the output is f of x or the output is x. If the output is x, then it is in A, and if the output is f of x, then because of this thing, again the output is in A. So we are never leaving A. We are forever trapped inside A, although we are saying that we are mapping A into B, but we are never leaving A. So if there is something else in B, that means outside of A, that can never be the output for any input under G. In other words, G will not be onto. Let's write this. If D0 is non-empty, i.e., if A is a proper subset of B, then G is not onto, since G of A is actually a subset of A. So we modify the definition of G by swapping A and B and keeping everything else the same. So what we are doing, that instead of this Now we are doing this. The definition, that is the rule defining G, we keep it the same. But we have to again see whether this makes sense, because previously we saw that there was no problem with the definition, at least. There is this problem only. But now we have swapped, we have interchanged the positions of A and B. Now is G well defined? Let's see that first. So now we are going to choose our X from B. Okay. So again that same thing. X either lies in this union, in that case the image under G of this input X is f of X. Since f originally maps C into A, so this f of X is a unique element in A. Fine. And if X does not belong to this union, okay, note this carefully. If X does not belong to this union, then what? Then in particular, X does not belong to D naught also, because D0 is one of the sets in this union. So that means since X is in B and it cannot be in D naught, so X is forced to be inside A. And the output is also X. And we are saying that we are mapping B into A. So here also we get a unique output in A. So the function here in this case also it's well defined. But did you see that in this case, that is if this condition is true, then X not being in D naught plays a role in putting it inside A, so that we ultimately get a function from B to A. We are of course not going to say this much here. We will just simply say one can see that G is well defined. G means our new G, okay, with A and B swapped. One can verify that G is well defined. Okay, so let us now show that G is two things. G is one-to-one and onto. Let's first show that G is one-to-one, that is injective. Let A and B be two elements in B whose G images are the same. I think now I can erase this part. Such that G of A is equal to G of B. To prove one-to-oneness, we have to prove that A is equal to B. But now the cases will come, because G is partly defined. If A and B both belong to the union, then f of A is G of A and f of B is G of B. But we already know that f is a bijection and hence an injection. And so, by injectivity, of f, A must be equal to B. And there is another case. Actually there are others, but this is another case. If both A and B are not in this union, then then G of A is just A and G of B is just B. So here we get more directly and quicker than that case that A is equal to B. But there are two other cases also. No? In one of them, A belongs to the union but B does not belong to the union, and in the other, A does not belong to the union but B belongs to the union. Those two cases are similar, so we need to consider only one of them. Now, let A belong to the union but B does not belong to the union. Then what do we get from this condition? G of A equal to G of B. Then, okay, so if because B does not belong to the union, so B is equal to G of B. But G of B by our assumption is G of A, and since A belongs to the union, so G of A is just F of A. Now look at this condition. Since A belongs to the union, so A will belong to some Di. Now since A belongs to the union, A belongs to Dn for some natural number n. Okay, and actually this n may be 0 also. That possibility is also there, although we did not be scared of that. A may come from D naught, because keep in mind that now we have chosen both A and B from capital B, and so that possibility is there that A may come from D naught. But what is important here is to notice this. Since Dn plus 1, well, oh yes, we can, okay, we can write n plus 1 itself. No need to write the general one. Since Dn plus 1 is by definition f of Dn, we have f of A belonging to Dn plus 1. You can clearly see why. Since Dn plus 1 by definition is nothing but f of Dn and our small a is coming from Dn, so the image of A under f will lie here. That means here. Okay. But this has created a problem. This implies that what is f of A? F of A is nothing but B. B belongs to Dn plus 1. But if B belongs to Dn plus 1, then this condition is being contradicted. contradicting this. So this case does not arise, meaning that under the condition that g of b is equal to g of a, it cannot be that a belongs to this and b does not belong to this. Similarly, we cannot have this and this. That also will create a similar problem. But in the other two cases that we wrote first, that we handled first, we managed to prove that A is equal to B. So that means for any two elements A and B in capital B, if G of A is equal to G of B, then A is equal to B. This proves that G is injective. Hence, G is injective. Okay, now we come to the task of proving that G is adjective. Next, let C belong to A, because A is the range of G. Okay, now we need to find an inverse image of C in B under G. And for this, what we are going to do, so here also we will have to take the help of those conditions, because depending on those conditions, that is belonging to or not belonging to the union, only the definition of G depends. So here the things go like this. If C itself does not belong to the union, if C does not belong to the union, then C is equal to G of C. Now, okay, let's see for a moment if this makes sense. Where are we choosing C from? We are choosing C from A. So, because A is a subset of B, C is after all an element in B. And that element does not belong to the union of the DNs. So by the definition of G, G of C is equal to C. So fine. So we have found an element C in B whose G image is the chosen element C. I don't think I should mention here that C belongs to B. It's clear. So let C not be in this union. Okay. Oh, and what does this mean now? C is from A and C is not in this union. See, the moment we chose C from A, already that automatically means that C does not belong to D0, because D0 lies outside of A. D0 is disjoint with A. So this combined with this implies this thing. Then C does not belong to this, where now n starts from 1. Oh, okay, how foolish. I considered this condition and again I am considering this condition. What the hell? Excuse me. I should have considered this instead. I don't know what I am thinking. Okay. Now C belongs to A, and in particular C belongs to this union implies that C belongs to this union, because C being in A cannot be in D0. That part is still there, but I made the mistake there. Okay. So now C belongs to this, and so C belongs to Dn for some positive integer n. This positivity is important, since Dn is equal to f of Dn minus 1. This is where we have used this positivity, because D0 is not an F image. D0 is B difference A. But D1, D2, these are F images of the previous Ds. Because our n is positive, so Dn is f of Dn minus 1. So even if n has the smallest value 1, here we are looking at D1, which is f of D0. But for higher values of n, of course, we have Dn minus 1. We have, so C belongs to Dn, so that means C belongs to the F image of some set. So C will look like this, f of D for some D belonging to Dn minus 1. Now whatever Dn minus 1 is, it is after all a subset of B. The D's where the suffix values are positive are subsets of A, but D0 is not. But that is not a problem, because all the D's are subsets of B. So that means this D is coming from B. Thus, C is f of D, and this is nothing but G of D. That means in this case also C has been realized as a G image of some element in B. So G is onto. We have thus completed the solution. That is, we have shown that G is both one-to-one and onto, and as such G is a bijection from B to A, and hence B and A have the same cardinality. In the next exercise, which we are going to solve this coming Sunday, we will see that we can use this exercise, which is somewhat technical, to prove that in a situation, if you are able to find injective maps from set A into B and also from B into A, then there exists a bijection between them. This is Schroeder's theorem. So we will see how that can be proved, and that's all in this video for tonight. And this coming Tuesday we have another upload. So what shall we do on Tuesday? Let's go back to calculus. So see you on Tuesday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.